Okay. Good afternoon, students. You can enter your registration number in the chat box for attendance purposes. Okay. Okay. From the last few weeks, in fact, we are discussing basics of magnetism. I'll continue that even today. Hopefully next week I'll start introduce the experiments. We'll get started today, but then probably what we are going to do. I planning to record some videos also for the experiments, so that you get a first-hand information about what experiments you are going to do and things like that. Okay, and then eventually we'll share some data asking you to analyze that also as well. Okay, so to continue the discussion, I'll start sharing the screen now. Okay, and feel free to ask me any question that you have by unmuting yourself. Okay, because I will not be looking at the chat box, so please ask me directly. Okay, yeah.
Sir, on previous class we have talked about the magnetostatic energy.
Yeah, I'm
and
going to
also tell that domains reduces the magnetostatic energy.
We are going to start from there again. Huh? You reserve your question. I'm going to start from that point onwards. Right. Right.
Okay. Okay.
Yeah. You can still ask me if you're not. I mean, if you don't get your answer. Okay. Yeah.
Okay.
Yeah. Yeah. Can you see the screen now?
Yes, sir.
Okay. So what we were discussing last time is basically, I mean, domains are present in ferromagnetic materials, because of which we don't see that material is magnetic even though the temperature is less than Tc. For example, iron, which has Tc close to 1000 Kelvin, often is found to be not possessing any magnetic property unless it is processed because of domains. So we are trying to understand now why domains exist and what determines the domain direction, and how many domains you can have, and how by having domains the energy can be minimized and things like that. Okay, so for that discussion I am considering, even though I wrote here total, I am neglecting the Coulomb and other parts of energies. Basically I am looking at the spin orientation or magnetic configuration. Okay, I'm already assuming that it's a ferromagnetic material. Okay, ferromagnetic or antiferromagnetic, but not to confuse yourselves, let us restrict to ferromagnetism now. So I know that there are permanent magnetic moments, and I also know that these moments are interacting with each other, and we know that because of this exchange interaction, they prefer to lie collinear, because I already said that it is ferromagnetic, so Jij is positive. So the only way this energy can be minimized, nothing but this energy here, because this is a Hamiltonian I wrote here, but the corresponding energy is E exchange. E exchange corresponds to the energy associated with the coupling of the spins through exchange interaction. So this energy demands that the spins have to be parallel to each other. Okay, so this energy will be minimum as long as the spins are parallel, but it will not give you any direction, which direction they can be parallel. So if you leave it to this energy alone, it can be parallel in any direction, doesn't matter. Only thing it demands is that it will be minimum, this energy will be minimum if they are parallel. So that is where the second term, which talks about the anisotropic energy. To be specific, I gave example of magnetocrystalline anisotropy, but it's not necessary just that. There can be other forms also. We'll not go into details, but let us assume that we are talking about magnetocrystalline anisotropy. What does it tell? It tells that, okay, because of some spin orbit interaction, there are certain crystallographic directions depending on the crystal structure. Certain directions the spins prefer to orient. So those directions we said easy directions of magnetization. So along those directions, if the spins are parallel, taking term into the account of the first term, then the energy will be minimum. So if you add these two terms, what it tells is, okay, there are certain directions. Let us say cobalt. Okay, for example, in the cobalt we have seen that c-axis is the easy axis of magnetization. That is, the energy will be minimum if the spins are parallel to c-axis. Okay, so if the spins are parallel, not only parallel to each other, but also parallel to the c-axis, then that will take care of these two terms, minimizing the total energy. Okay, so that is preferred. So when I say c-axis, it is not directional, unidirectional. This is uniaxial. That means along c and opposite to c also, because as long as c direction is spins are pointing, but mind you that all the spins either have to be parallel in this direction or in this direction. So if you look at these two terms, they dictate that the spins have to be parallel along c. If I am considering c-axis, cobalt, which has a uniaxial anisotropy. But if I consider, suppose, iron, which has a cubic anisotropy, in that the cubic anisotropy tells that there are 3 crystallographic axes or 6 directions. Okay, because parallel and anti-parallel. So along those 6 directions, x, y, z, along those 3 axes multiplied by 2 directions, so 6 directions, if the spins can point parallel to each other, so that the energy can be minimum. So in fact, it so happens that in iron, the spins do point in all these 6 directions. So that is why you have domains. But then the question is, why domains? Why not a single domain? Why not they just be along parallel to x-axis? Let us say along to parallel to the edge, cube edge, and then all of them, let them be in the along the then the magnetocrystalline energy is small, is minimum, and exchange is also minimum. So what is the necessity that the spins have to be into domains? That's the question I'm asking. See, point is, I'm making it very clear here. We do have domains, but domains are not random. Domains do point along the easy axis of magnetization. Okay, so these easy axis of magnetization are dictated by anisotropic energy. So the question is, why do they point along different directions? That's where we started the discussion last week. I'll continue now. Okay, there are calculations. I will skip. I'll try to give you more in terms of no arguments, but I will share the calculations. Those of you who are interested can go through that, and still, if you have doubts, you can come back to me. Why I am not doing calculations is purely because we will be doing in the advanced condensed matter a little more rigorously. So that is why I'm trying to avoid now getting into the too many details. Okay, but I'll tell you. So yeah, someone actually, I think one student asked me, Ashik or somebody, I don't remember name. So you see, I am considering, let us say, uniaxial crystal. So in that, for example, cobalt, in which the c-axis is the easy axis of magnetization. So there are two situations. It can be that all the spins are parallel and pointing along the c-axis. Let us say that means it's a single domain. I'm considering initially a single domain. Let us say that means all the spins in the material are parallel to each other and pointing along the c-axis, minimizing the first two energy terms which we saw in the previous expression. Okay, but then what is happening is, the moment you have, you remember, you know very well, someone asked me this question, you know that even Maxwell equations tells you that the magnetic field lines have to completely close. That is what basically, you do not have a single kind of a pole. They have to, like your electrical charges, you can have a positive charge and negative charge, either the field is diverging or converging into a source or sink. But magnetic poles always, they occur in dipoles. Okay, so you need to have these field lines closing always. Okay, that is by rule. So what you have is, because of that, and before that, when the spins are all pointing along the direction, we can always show it as an arrow, and the convention is that arrowhead basically points north and then arrow tail points south. So I can always say that, okay, there is a surface and you have these surface poles. That means basically there is an accumulation of set of north poles here, there is an accumulation of south poles here. In between, of course, they always have. So since field lines have to close now, you clearly see that these field lines will basically emanate out from the north pole and then they close into the south pole. So you see, inside the magnetization is pointing parallel to this arrow, whereas the so-called fringe field or the residual field, or the field which is sort of emanating out from the so-called surface spins, surface poles, is pointing in a direction opposite to the internal magnetic field, okay, or internal magnetization. So you can consider now two kinds of fields, okay. One is the internal field, which is responsible for the spins pointing along this direction, parallel to this direction, which we call a Weiss molecular field or Heisenberg exchange field or interacting coupling field or internal field, whatever you call. I mean, this is basically, this is doing exactly the role of an external field. I have not applied any external field now, mind you. So this is simply, this field is coming because of the, it's like, chicken and egg. So it is, the orientation is there because of the internal field. Our internal field is there because of the coupling between the spins. So they are like, mutually, I mean, cause and effect of both. Okay, in that sense, there is an internal field because of that, and that internal field is pointing along this direction. That is what is making these spins parallel to c-axis, right? So this is one field in that you can understand. But now, because of the so-called surface poles, you see that these will have a field. If I call this is anti-parallel or opposite to the internal field, and this is purely coming from the surface poles. So since if I assume that the internal role of internal field is to magnetize the specimen, so that you have a net, if I can take average m, okay, that is finite, okay, domains, only single domain, so this is finite. If I say that, then this is internal field is, if I'm saying it's magnetizing the specimen, then since this field is opposite to this field, I can use the term that this is a sort of demagnetizing. So if I am trying to magnetize the specimen, or not by applying external field, if the interaction or coupling is trying to magnetize the specimen by aligning them along a particular direction, as a result of which the induced poles which are generated will create a field which is trying to sort of demagnetize the specimen. Okay, you may ask, sir, what happens to whether it will magnetize or demagnetize? No, it will still be magnetized. Only thing is, this is like a correction, small field, because we are not really looking at a bulk sample. Of course, when you go to nanomaterials, things will be different. I'm not discussing about that. We'll talk about that much later. Okay, since in the bulk, what you have is the number of these surface poles are much smaller in comparison to the large number of dipoles which are oriented, or spins which are oriented along this direction. So this is only a small correction to the total field. So if I write the total field seen by the spin system, I can write this as, if in the absence of external field, internal field minus the field due to the demagnetizing or surface points. So this energy, this is sort of called self field or magnetostatic energy. So this magnetostatic energy of a single domain crystal can be written as half Nd ms square, where Md is basically the magnetization itself, magnetization square within that domain, and Nd is the demagnetizing factor. So this actually can be calculated based on the dimensions of the material and the shape of the material. Basically, it tells you that how many surface poles are induced and all. I forgot to include the expression for that Nd. I will give you a source. Okay, you can calculate. Suppose given a source, given an oblate, given an ellipsoid, given a cube, given a square, given a sphere of some certain dimensions, you will be able to calculate Nd. Okay, so you can calculate Nd, and then basically it gives you a magnetostatic energy. But the total thing, nx plus ny plus nz is equal to 1. This is like normalized to 1. Basically, the total demagnetization factor along, say, let us say x direction, yz direction, plus z direction, everything is 1. Or in CGS units is equal to 4 pi. Okay, in the SI units is basically 1. So the if I actually substitute that, the magnetostatic energy basically comes out to be 2 pi in CGS units, 2 pi ms square L, where L is the thickness of the sample. Okay, so this magnetostatic energy you see is proportional to ms square. So if there is a way that actually I can break down into domains, let us say for a minute that I have two domains. then what happens is naturally ms square is reducing, because within the domain the net magnetization is smaller in comparison to the net total magnetization that's there in the single domain. So thereby the magnetostatic energy is decreasing, or the self energy is decreasing, or the demagnetizing energy is decreasing. Okay, so you go back to this expression, you see that exchange plus ek plus ems. So having lowered these two fellows, our emphasis is to reduce ms. Okay, forget about this for a minute. So how do I reduce ms? Okay, so I say, okay, if I break into two domains, then I can reduce ms. But then when I break into two domains, what happened to exchange and AK? Will they remain the same? Will they also get affected, or will they remain the same? So we'll look at that point now. We'll say that, but see, exchange, if you see within the domain, forget about now the other part, within a domain, if you look at it, they are all parallel. So per se, if I simply consider this, exchange is not changing much. It's not changing actually. If I forget about this line which is separating these two fellows, I will go to that in a minute. But within a domain, exchange is not changing, and magnetocrystalline anisotropy is also not changing because spins are all parallel to c-axis. But ms is decreasing. And this is also true for the second domain. Second domain also exchange is the same, because exchanges, they are parallel, so it is minimum. And so is ek, that is a anisotropic energy, and ms is decreasing. So by breaking into two domains, you can in fact reduce the magnetostatic energy very much. Okay. Then you may say, okay, if that is the case, why don't I break into further domains? Yes, you can break into further domains, let us say 4 domains. Then again the same rule, basically you can lower. But then now what you do is, I'll take questions after for next slide. Okay, so so similar thing can happen if I'm considering a cubic crystal. Okay, you see that here the number of surface poles, like the fringe field is actually decreasing. Instead of having such a large field, the field lines are able to close here, field lines are able to close here, so fringe field is decreasing. And this is a special case, which is a cubic crystal, in which, because the magnetization can point along 6 directions, here I need actually only 4 directions, like let us say this is like 001, and let us say this is like 100. So I can say I can have 001 and 001 bar, 0 and 100, 1 bar 00, and say same is the case here. So I can, that is, the domains or the spins can orient in these directions. Thereby there is, in fact, in this particular case, we call this as a closure domain. So no magnetic free poles are there and no magnetostatic energy. In fact, magnetostatic energy in this particular case is 0. So you cannot minimize any further. Okay. So this is the minimum energy that the system can have. And what happens to exchange? Exchange is minimum because they are all parallel within a domain, and magnetocrystalline energy is minimum because they are all pointing within a domain. They are all pointing. I mean, all the domains themselves are pointing along easy axis of magnetization. So there is no the energy will be minimum. Okay, but I am cheating here. Why am I cheating? Okay, we'll come back to that. So the sample is in a single domain state. There is a large stray field which I talked about, which is called self energy, and formation of domain reduces the stray field. There is a formation of closure domain, ensure that the stray field, hence magnetostatic energy is 0. So I said I am cheating. Why am I cheating? Here, see, this is one domain. This is another domain, which I'm actually magnifying glass. I am actually looking at it now with that line which I showed you earlier. This line is not such a sharp line, which is separating it out here. Okay, so I am sort of now magnifying this area, and then I see that area is like this. So what you have is, suppose in this domain, this is one domain in which the spins are all parallel, let us say along 001 direction. And let us say domain B, where the spins are all parallel, again they are all along like minus this direction. In fact, 001 bar I should have written. Okay, so 1 bar. So as far as this domain and this domain is concerned, exchange and anisotropic energy both are minimum, so no problem. And we also reduced magnetostatic energy because we divided into 2 parts, so the net magnetization is decreasing, thereby magnetostatic energy is also decreasing. But now when I look at it here, you see that to flip from here to here, you need large energy. I told you last time that it basically costs 4Js square, which is quite large. In fact, if you calculate, so what it does is basically it tries to. I'll give you a mathematical expression in a minute. So system prefers to actually this flip to take place over a number of spins. Okay, if you can actually divide this over number of spins, then the cost in energy will be minimum. I will show you why it is so, but you please listen now. So that the energy can be minimum if this flip is spread over a number of spins, and which is what this is what happens in real material. And in a real material, the region over which this flip takes place is called block wall. Actually, domain wall. I should not be saying block wall because there are two different kinds of domain walls. Depending on the orientation, there can be block wall or Neal wall, but I'll not go into those details now. I'll only say that the gradual rotation of magnetic moments occurs over a region, and the region which separates out these domains is called domain wall. Okay, so what happens in a domain wall now? Can anybody tell me what happens in the domain wall? What do you think will happen because of this domain wall now? Unmute yourself and tell me. With respect to the energy, what is happening in the domain wall? Are you there? Am I audible?
So decreasing.
What is decreasing? Let me go back to my.
Sir,
I want to see you people. I admit somebody is waiting for enter. Yeah.
Sir,
Yes.
energy is discontinuous in the domain wall, sir.
So why is it
function of energy? So
why
sir, it's flipping means we can say there is sir, like it's a discontinuity over that point.
No, we are not looking at a single point. What I'm saying is because of the creation of domain wall. See, I cannot have a domain. I cannot split into domains without creating a domain wall. You got it? Because yes. I cannot have one domain like this, parallel, then anti-parallel. No, because this sudden flip will cost too much energy. We checked last time. I basically consider 3 spins parallel. Okay, one of them if a flip, then you saw that the total change in energy would be 8Js square. It is a really huge, large change in the energy. Okay, so yes. Whereas if it is spread over a number of spins by, let us say, by n spins, the same pi, then that energy will decrease by factor of n. Okay, so that is why you have a domain wall. But then when you have a domain wall, I am looking now only at the domain wall. I am not looking at domains. So what happens to the exchange? Can you tell me? What happens to the exchange term within the domain wall? Yeah.
Sir, energy will increase.
Increase. Ashik, and you say energy is increasing. Which energy are you talking about? Ashik?
The exchange energy will increase because they are
not parallel. They are not parallel, right? Their exchange will be minimum when phi is equal to 0, isn't it? Since phi is finite, exchange energy will increase, right?
Yes, sir.
Yeah, but if the exchange energy, the increase in exchange energy, if you want to minimize, let us say, of course, I have to increase, there is no choice because it has to finally flip, but I want to decrease the increase. You understand what I'm saying? I want to minimize the increase. So what do I do?
Only small difference will be there.
Yeah, Sudaman is saying something.
Like we have to twist it very in small angles.
Small angles. That means I have to spread it. I have to stretch this twist over n tending to infinity. Suppose if I do it over the entire sample itself, let us say, then the change in energy will be minimum, isn't it? Right?
Yes, sir.
Yes. All of you are following? So, but then in the process, what happens? The entire sample becomes a domain wall. Right? Because I would like to spread over in n spins, n tending to infinity. Okay, but then I have to consider about the second term now. What happens to Ek?
Increases.
Ek increases. Why?
Because you are pointing in all directions.
All directions, not just the easy directions. So if I leave it to exchange alone, it prefers n tending to infinity. Okay, let us assume exchange separate. If we leave it to Ek alone, what happens? If I consider only Ek, I don't bother about exchange. So what do you think will happen?
They turn quickly.
N tends to 0. because they would like to, they don't want more number of spins to deviate away from the easy axis. Are you getting? How many of you are following this argument? Okay. See, you want to break into domains because MS is dictating. That is, magnetostatic energy is dictating. But then you have to satisfy, beforehand you have to satisfy both EX and EK. So EX is demanding that n should tend to infinity, and EK is demanding that n should tend to 0. So how do you solve this problem? You have to minimize the total energy anyway. So what do you do?
Sir, in between energy will be minimum.
Sorry? Hello?
In between two cases, energy will be minimum.
Minimum, correct. Okay. So you basically, you dou E by dou width, the delta we call, delta meaning the domain wall width. So you minimize with respect to the width. So write the expression and then differentiate it and equate it to 0 so that it's minimum. So you get some width. So that means, what does it tell you physically? Physically, it tells you that it will be a of course, there are two competing terms. So you sort of, the domain wall width will be such that it is the minimum, I mean width, which will satisfy both the conditions. Okay. But nevertheless, creation of domain wall will always increase the energy. Okay. So it will increase the energy, but then why will it create a domain wall? It will create a domain wall because it has to break into domains. So as long as creation of a domain wall decreases the net energy, because by creating a domain, you are decreasing the magnetostatic energy. So if you can decrease the net energy by lowering the magnetostatic energy, even though there is a small increase in the exchange because of the finite width, and also small increase in the EK because of a small finite width again, system prefers to break into domains. So every creation of a domain wall will cause some energy, but nevertheless, since the magnetostatic energy is decreasing, there is a preference to go into domain, create a domain wall. So what it does is, system actually now breaks into domains so much so that finally further creation of one domain wall will change the balance. So if I create now, I told you, right, I have made first two domains, then I said I made into 4 domains. So then I can go to 8 domains, but then probably if I create 8th domain, the equation is such that it will, instead of reducing the total energy by decreasing MS, magnetostatic energy, because of increase in exchange and anisotropic energy, the energy may increase. So that sets the limit on the total number of domains as well as the size of the domains, because once you put the restriction on the number, then that also restricts the size. So now you understand. See, domain wall width is controlled by these two fellows, EK and E exchange. Okay, but the number of domains or the size of domain itself is controlled by the net energy, total energy. Okay. Any question on this?
Sir,
yeah, hello, yeah.
Sir, when we are breaking the domains, we are telling that magnetization is decreasing.
Yes.
In a particular domain.
Yeah.
I'm not
because
getting
that's it. Look, what is magnetization? Magnetization is nothing but
magnetic moment.
Magnetic movement per unit. I mean, net magnetic moment per unit volume, of course, magnetization. But here
Yes,
we are
sir.
considering within the domain what is the net magnetization. Okay, so that is what we are saying. This is not the average magnetization I'm talking about. I'm talking about only within the domain. Okay, so if earlier there were so many domains, so many moments, so everything was pointing up, right? Everything was, so the net magnetization was high. But now, since the area is restricted, I mean, per volume, of course, it may still remain the same, but
Yes, sir, that's a point.
Summation, we are looking at just the n mu I in this case.
So that was my point, that in a particular moment, magnetic moment is volume is decreases, so it should be constant.
Huh?
in a particular domain,
Yeah.
we have reduced the magnetic moment. Also, we have reduced the volume.
Yeah.
So
See,
it should be constant.
that is true. That is true. But what we are considering in this expression is that that n factor is also coming. That actually which will take care of the fringe field or the surface dipoles that are there. Okay, because the surface poles now are the fringe field is decreasing. Okay, because the field need not really go into the space to extend the to close the walls, which I showed you. I mean, through this picture, you see that I showed you here. I'll go back here. Let us say, okay, here you see in this picture, you see that this is basically the demagnetizing field to start with. Okay, so this basically will get reduced now because there is a possibility to close here itself. So the net magnetostatic energy, for the same reason, it's basically the controlled by the surface poles. As I told you in this case, since there are no magnetic free poles, we are not really looking at per se magnetic magnetization alone. Okay, it is related to magnetization also, but more importantly due to the surface poles. So in this case, since the surface poles are not there, there is no question of any magnetostatic energy at all. Okay.
But some magnetostatic energy is not only due to the surface charges.
No, magnetostatic energy in this case, what we are considering in this expression is purely due to the surface energy. If the surface
Okay.
poles are not there, it is not there at all.
Oh, you were considered like that.
Yes.
Okay.
Yeah,
Thank you, sir.
because the other fellows are already there. Exchange and other things are already there. They are taking care. They are taking care of the alignment and the net magnetization. I am interested in only because see, for example, in the exchange, if you see, okay, this SI and SJ, they talk about the movements per se. Okay, so that is already taken into account. I am not looking at that energy. This energy deals with only the surface poles or induced poles because of the internal field or external field. If you apply the external field also, same thing will happen. Okay.
Yes, sir. But in the expression of that, you have taken in the term of magnetization.
Yeah, it actually goes with respect to see MS again. I mean, that is true. What you are thinking is MS, but what you also see is that it also has terms related to the shape factor. Okay, and this shape factor will bring in the surface pole density.
Okay, good, sir. Thank you, sir.
Yeah, no problem. Okay, see, okay. Anyone has any question why this particular shape? What do you observe in this shape? Can you tell me? Apart from closure domains, do you see anything peculiar? I'm talking about this picture. Do you want to ask any question by looking at this picture? Okay, I myself will ask and also answer. Okay, what do you see? You see that there are two kinds of domains, isn't it? One is elongated, like vertical domains. Let me put it, if I can use the word. Okay, that means along, let us say because this is cubic crystal, so there is nothing like okay, for z direction, let us say, if I assume or this is actually 0 1 0, so maybe y. Okay, so this along this vertical direction there are domains, and along this horizontal direction there are domains, isn't it? And what you see is, if you closely observe, that these vertical domains are have more volume, are bigger in size in comparison to the horizontal domains, which are occupying a smaller region. Okay, why do you think so? I mean, don't you think it is little odd? Because we never discussed anything what decides the domain size. So why suddenly why they are not equal? For example, in this case, let me go back and see. See here, I actually divided equally. Okay, I did not put this. I did not push this wall the other side, saying that okay, this fellow is smaller than this. No, when I even divided into 4 domains, I still did them equally. Okay, so all of them are having the same kind of a volume. Okay, but when it comes here, suddenly I have decided to divide them having a longer vertical domains in comparison to the horizontal domains. So any clue? Why do you think this is coming into the picture?
Or is it due to anisotropy?
Anisotropy will only say that easy axis of magnetization, the spins have to be parallel. Okay, and this being cubic, this direction is also easy axis and this direction is also easy axis. So easy axis will not differentiate whether the spins are pointing along this or this. So they will not restrict so-called, the growth or size of the domains. Okay. Any other? Yes. Okay. So I wrote another term here. Right, the fourth term, which is the magnetoelastic energy. So that actually is coming into the picture and deciding the size. Why? Why? Because whenever you apply a magnetic field, because of the spin orbit interaction, the dimensions of the material also will get affected. Okay, they can be positive mostly, and sometimes it can be negative also. So that means that property of changing the dimensions of the material with respect to the application of magnetic field, okay, is called magnetostriction. Okay, this is basically elastic, magnetoelastic property. So the dimensions are changing. So what I'm, okay, you may say, when I say application of magnetic field, it's not necessarily external magnetic field. I am telling again and again that the internal field for a ferromagnet does exactly the same job as the external field. So when I am discussing here, I'm actually discussing in the absence of external magnetic field. I did not apply any external magnetic field. Whatever field I'm talking about is purely produced by the interactions of the spins, which is nothing but the internal energy. So because of the internal energy, it can be a magnetoelastic energy. So what happens is this energy also has to be minimized, which we never discussed so far. Now we are discussing. So the role of this fellow is to make sure that the energy is minimum. So what happens is, suppose if I have now, I will not give too many details, but I'll just give a physical argument here. What happens is, if all, see what happens is when you apply the magnetic field, the spin specimen can try to elongate along this direction. Okay. And at the same time, because of this orientation, the domains will also try to orient along that. So there will be actually a friction, basically a strain which is developed at the domain boundary. Because on one hand, this domain is trying to grow this way. On the other hand, this domain is trying to grow this way. So because of that, there is a magnetostriction, and also which arising because of that, there is a strain or a strain in the material. So this strain can be minimized if we have a particular variation in which the domains are oriented, longer. It can be in this direction, or I can rotate by 90 degrees and say that horizontal is longer than the vertical. It's only the way in which you look at it, doesn't matter. It's only thing that basically the closure domains will always be, the closure domain means the domains which are actually making sure that there are no surface poles will always be smaller in size in comparison to the larger domains. So to make the magnetoelastic energy minimum. So that is the role. So this shape is coming purely because of magnetoelastic energy. So I'll not go into more details in that, but I'll come back to this point here. Suppose exchange energy alone is there, it prefers a wide wall. Okay, so you would like to have this fellow will be small, that means the exchange energy will be small if you have a very wide wall, and if you have a very thin wall, that means immediate flipping, then the exchange energy will be very large, which we discussed. So I will actually, So I will go to this step. So you know that exchange energy is given by SI dot Sj. So if I say that S is the spin on site I and J, both are equal to S. And if I say phi is the angle between the Si and Sj, so the energy associated with that would be minus 2js square cos phi. And I expand this when the phi is small, I can simply do a Taylor series expansion and then I can substitute it. Then you get js square phi square minus 2js square. And you see that this minus 2js square term, the second term, is independent of the angle and which will have a minimum energy anyway, minus 2, so you cannot do. So this term basically decides the change in the exchange energy. So the extra exchange energy existing within the domain wall is given by the first term, and that is js square pi square per spin pair. So I can actually, so if what I do is, as we discussed, now mathematically I am writing, I can actually make this phi smaller by having divided this pi over n spins, n being very large. So if I make a 180-degree domain wall, in fact, I can have a 90-degree domain wall for the closure domains. I'm not doing that. I'm taking only uniaxial case. I have a 180-degree domain wall. So what I mean by 180-degree domain wall is, again, I'll just make it clear that the domain wall which is separating these two fellows. Okay. So for example, sorry, going back and forth. Yes, here. This domain wall, this one which is separating these two fellows is 180-degree. And this domain wall is 90-degree domain wall. So, okay, so I am calculating the energy associated with the 180-degree domain wall. And it becomes easy for a uniaxial system. Okay, if you consider a cubic crystal, it becomes very clumsy because there are two terms which I have to take. I'm just showing for a easy thing. For a uniaxial case, then what happens is this becomes pi by n. And if I substitute that in the previous expression, then I will get js square pi square and n by 1 by a square, a being the dimensions basically, okay? N atoms per unit area of wall, and then there will be 1 by a. A is the lattice dimensions if we take. Then it becomes some term here. So essentially what you get is exchange is proportional to 1 by n, which I already told you, okay? Exchange is proportional to 1 over n. And anisotropic energy is proportional to k, n itself, where k being the anisotropic energy per unit volume. So n is the, so this fellow will be larger if n is large. That means more spins are deviating away from the easy axis. On the other hand, this is directly proportional and the previous one was inversely proportional. So as we discussed, we have to minimize the total energy. So this gamma basically is the width, okay, or the sorry, energy, which delta is the width, okay. Delta, so you have to minimize this change in the energy with respect to the domain wall width. So you see that one fellow is decreasing, another fellow is linearly increasing. So you hit upon basically a point where this is called basically domain wall width. Okay, so this delta is the domain wall width, which is given by this. I will share this. You can go through this calculation. Okay, it's not very difficult. So you see that the smaller the anisotropic constant, the thicker the wall. So that is the point. So I will skip now. You can actually plug in some numbers for a given system. For example, iron, which has 1034 Kelvin as the TC. This is the anisotropic constant. This is the lattice constant, basically, lattice constant. So you can plug in and say that what would be the n over which this flip takes place for 180-degree domain wall, and what would be the typical domain wall width, which comes out to be something like 300 angstroms. So you can actually calculate these kind of things. Okay. So what is the energy associated also you can calculate. I am not. So now we'll come back to this next step is how does the magnetization takes place. Okay. So to start with, intrinsically, because we discussed it so far, to minimize the total energy, the system prefers to break down into domains so that the net magnetization most often will be zero. Okay. If you have not done any processing to the material. Okay. That means you have not applied any magnetic field. Now, so at an ambient temperature, it basically even below TC also, even though it's a ferromagnet, the net magnetization, if you simply take a nail on the road, which is iron, which can still have a net magnetization 0. So that is what is the origin here. Okay, so this is the magnetization is 0 when the external field is 0. But when you apply the magnetic field, the magnetization actually grows initially, okay, and then it grows very fast, and then finally it saturates. So there are two processes mainly which are involved in magnetization. What are those two processes? The first process is basically deals with the domain wall motion. That means the domain which is to start with oriented along the field direction. Okay, suppose you have applied the field, let us say some direction, but there may be a domain which is already pointing in the direction. Okay, because intrinsically, assuming that you have applied the field along easy axis. Okay, if it is hard axis, okay, there may not be any domains, then you have to do more work. Then this curve will not grow so fast. But I am assuming here that I have applied the field along the easy axis. So some domains are already orienting along that, but some of them are oriented anti-parallel to that, or if it is a cubic crystal perpendicular to that. So that kind of a thing is there. Then what happens is the domain along which the field is applied, that will grow. Why? Why? Because there is an additional energy which comes into the expression now, that is nothing but your Zeeman energy minus mu dot H. Okay. So that energy will be minimum if the spins are parallel to the magnetic field, applied magnetic field. So this domain will grow at the expense of others. So the fellows which were not in the direction of the field will basically shrink in size, and this fellow will grow. That means in the domain wall, you have seen here. Okay, I'll go back to this picture. In the domain wall, yeah. Suppose I started applying the field in this direction, let us say. So this fellow, this line will simply slide towards my left, so that making more and more fellows pointing along the field direction slowly. Okay, till this line appears here. Okay, so this fellow will increase. The domain basically will grow. So that means the domain A will grow now. Then finally, the domain B will bodily rotate at very high fields. At the very when the field becomes really large, then that is not at all energetically favorable. So the domain B will bodily rotate. So that's called domain rotation. So basically, you have a wall motion followed by rotation will bring the magnetization to saturation. So when the domain B also points along the field direction, then everything is pointed. So then there is no further increase in the magnetization, and the material is said to be saturated. So that is what happens. I can show more microscopically here. So you have so many domains initially. So domain wall movement takes place. So I have applied field in this direction. You see that slowly the other fellows are rotating. Finally, everything is rotated in this direction. So there can be different processes. In fact, there can be irreversible rotation followed by initially domain wall movement, so that they are basically growing in size in comparison to the other fellows, and finally the magnetization will grow. So similarly, this happens. I show you another picture here. This domain A is growing. Finally, this fellow will rotate, and and then magnetization will take place. So the magnetization, if you see, if you actually plot it, you see that the magnetization will start from 0 and then go and then get saturated. But then you see that this fellow, actually this domain wall motion is, if you put a loudspeaker there, you can hear some tick, tick, tick sound also. In the sense, this is called basically Barkhausen effect. So because the domain wall motion takes place in jerk. Okay, so nothing happens, then suddenly the magnetization energy is increasing, then suddenly there is a movement. Then because if there are defects or some impurities or something is there, this domain wall actually gets pinned. So it will move in jerks. So that is what is actually shown here. So this will happen. But now when you are decreasing the energy, okay, so that means you are actually decreasing the magnetic field. So what happens is, because the spins are all coupled, so they try to prefer to orient in this direction. So when you are actually decreasing, system it's not free to rotate along the field direction because of the ferromagnetic coupling this system has. So you need to spend more energy. Okay, even if you decrease the field to 0, there is still a remnant magnetization. You see that there is actually still only a few portion is basically small portion is, there is a small nucleation of domain and a small portion of magnetization is switched, but not the entire thing. They are not equal. Okay, so there is a large portion of magnetization pointing along the field direction because of the coupling between the spins. Thereby, there is a finite magnetization which is present even when the field is 0, and this magnetization is called remanence magnetization or remnant magnetization. And to make this 0, then you further increase the field in the opposite direction till it hits upon a field called the coercive field. So this field is called the coercive field, where again it will go back to the original configuration of unmagnetized state. Okay, so there the net magnetization again is 0. So now what is happening is, because of the field in the being opposite direction, then again the domain's nucleation will take place, which will minimize the energy, which are parallel to the field and opposite to the field. So again you go back to the 0 state. Then further increase in the field will again replicate the same procedure, and then you will get something called hysteresis curve. So this is basically the process in which it happens, and you see such a beautiful hysteresis curve. So this is basically initial magnetization is like this. So the red line shows the initial magnetization. From a 0 magnetized state, you can all the way saturate it, then bring back the field to 0, you will get MR, then bring back the field to negative field, then to HC, your M becomes 0, then you hit upon a negative saturation, then come back here, then MR is again, you will have MR here, then again go back. So in a normal ferromagnet, I'm using the word normal ferromagnet, the Hc plus, that means the positive direction, the field which is required to make the field magnetization 0, and the Hc minus, both are equal in magnitude. Okay. Similarly, Mr plus and Mr minus are equal in magnitude. So this curve is symmetric with respect to the origin. So that is the usual, I mean, in general for a ferromagnetic material. Okay, if time permits, I'll tell you some other examples, but this is precisely the typical magnetization curve that you see. And based on the shape of this curve, and also based on the values of these remnant magnetization and coercive fields, these magnetic materials can broadly be, when I say magnetic materials, I am using the word now, I am all discussing about ferromagnetism only. So don't get confused, don't confuse yourself. We are only looking at ferromagnets. So ferromagnetic materials can broadly be divided into two categories, namely hard magnetic material and soft magnetic material. So what I mean by hard and soft, it's not the mechanical hard or soft that I'm talking about. It is soft when I say easy to magnetize. So something very easy. I don't need to really apply a large field in order to magnetize the specimen. So for example, this inside one, what you see here, you see that for a very, very small field, I am able to magnetize the specimen, and then I am able to demagnetize the specimen again for a very small field. That means the Hc in this case is very, very small. Okay, so the Hc is very, very small. So this material is called a soft magnetic material. On the other hand, you see another curve, the outer curve, where you need to apply reasonably large field in order to saturate the material or magnetize the material. And similarly, you need to apply a very large field in order to make the magnetization 0 or switch the magnetization, okay, in the reverse direction. So this material is hard in the sense it required more energy or more field in order to magnetize or switch the magnetization. Okay, so this material is called hard magnetic material, and both have completely contrast applications. Both are very, very useful. In soft magnetic materials are useful, and also hard magnetic materials. What are the applications you have? For a soft magnetic materials, they are used in transformer cores. Okay, you want to use the AC field in order to reduce step up or step down transformer, because the area under the curve normally in a AC cycle refers to the loss, magnetic loss. Okay, so that energy is liberated as heat, in fact. So that is like you want to minimize, when you want to actually use a transformer, you want to minimize the loss in energy. So you would like to have a material which has very, very, very small hysteresis curve, okay, or a small coercive field. So you should be able to back and forth the switch without much of much of a loss in the energy. So these materials are very good for transformer cores, and also these materials are soft, so magnetic field lines can penetrate through easily, and so they are like very, very good shielding materials. What I mean by that is, that most of the electromagnetic noise you will have actually, like when material is brought, a phone is brought into another phone close to that or something like that, you will see that there is an interference. Okay, so this interference can be avoided, electromagnetic noise loss can be avoided if you use a very high permeable material. If you shield the device or the whatever that you want to shield from the electromagnetic interference with a high permeable material, that means high permeability means the magnetic field lines prefers to go through the material than space or outside. So then what happens is all the field lines will go through this high permeable shield and leaving the inside device free of electromagnetic interference. Okay, so they are very, very useful in that sense. So for magnetic shielding, these soft magnetic materials are useful. On the other hand, if you want to use a permanent magnet applications, okay, permanent magnet means you would like to have some magnetic field, okay, present all through. So that magnetic field should not be immediately switched back, or it should not become 0 for simple perturbation or simple disturbance or simple thermal energy or anything. Okay, so those materials those applications, permanent magnetic applications, are motors and sometimes recording also. You would like, because you store the data, suppose I mean this recording, of course there are certain things, I'll come back to that, but you definitely do not want something to know, like when I write data into zeros and ones, in you know that in magnetic coding we write in terms of spin up and spin down. Like let us say spin up is 1, spin down is 0, so all my data can be stored in ones and zeros. So you should not, you don't want that ones to become 0 and zeros to become 1. That means this switching should not happen just because I pass by another magnet, or I do a tap something, or there is a thermal energy. So this switching should not happen with such a small perturbation or change in energy. So that, unless I want to change it, okay, I may want it to change, but I would like to change it by doing something. Okay, so that recording, whatever I did, should be preserved. Okay, so the data should not be lost, or the permanent magnetic field should be present. So under those applications, I prefer to use hard magnetic materials. So these magnetic materials are in general will have a very large coercive field and will also have a large permanent magnetization. So that is the kind of a definition that I have. So I'll take a couple of questions here if you have any. How come 34 students? Initially some 45 and odd have come and then they left. Why is that? Is it boring? Someone has to volunteer to answer.
No, sir. There might be some network
issues, I presume. Okay, dil ko khush rakhne ka. I feel that because of network issues they are not there, right? Okay, anyway, any questions?
Sir?
Yeah.
Sir, in that hysteresis loop,
Yeah.
After completing one cycle,
Mm.
suppose we did the second cycle, will the graph will be same, means coincide, or will it displace?
Wonderful, very good question. See, as long as you do a major hysteresis loop, so there are two kinds of hysteresis loops. Okay, so that means I can actually go back to the presentation and then tell you. Here what I am doing is, when I say major hysteresis loop, I actually traverse all the way up to saturation, then come back, then I do a complete again. So this is called the major hysteresis loop. But I could have done something else also. You see, I go here, then come back here, let us say finish. There's a small hysteresis. I only up to here. Or I go up here, sorry. Sorry. Okay. I go slightly up, then come back and then close. So these kind of, so I can actually measure many such small loops. Okay, so these small loops are called minor loops. Okay, so these minor loops will not be really reproducible. When I do it again and again, I may get, because I am leaving the state in some undefined state. Okay, the domain is in some undefined state, so it may not be, it may get pinned, it may not be free, so I may not be able to reproduce it. Okay, so it can get shifted, it can have all sorts of things. But as long as I am able to traverse the major hysteresis loop, that means I actually completely saturate the domain, then come back, and then domain saturate it, and then come back here. So if I do that, then most often, okay, only special cases, special materials, of course, there are some effects called training and all, that means the history dependent effects, but otherwise simple ferromagnets, because we are discussing simple ferromagnets now. So for those materials, the major hysteresis loop is always retraceable. Otherwise, there is no point. I mean, you measure today and then you report me some coercive field and remnant magnetization, and I do it tomorrow. If I get some other numbers, then this measurement has no meaning. Okay, because I am going to now introduce you to that experiment called BH experiment. So what we are going to do is we are simply going to apply the external field and then measure this hysteresis loop, and then derive information about the material, and then based on that I can actually tell a lot about the material, because you have seen just now. Okay, if I can tell first whether it is a ferromagnetic material, or whether it is a soft ferromagnetic material, or whether it is a hard ferromagnetic material, by just looking at the hysteresis loop. And also based on that I can choose the real application. So somebody, my lab, someone makes a material, then the first thing that I do is after characterization, I go and take a hysteresis loop. And then by doing that, I know what is the saturation magnetization, what is the remanence, and what is the coercive field. So then accordingly, I can say that, okay, my material is good for this and not good for this. You understand? So it is such an important characterization technique in order to distinguish or qualify magnetic materials for a given application. So in that sense, these material, this data is basically, that's why to answer your question, this is, yes, if you do a major, in fact, you have to do a major hysteresis loop, and then whatever data that you get, you record it, and that becomes a fingerprint for that material. Okay?
Okay, sir.
Yeah. Any other question?
Sir, is those coercivity values or it depends on the material or external magnetic field?
No, not external magnetic field. See, this is all material.
That means
see, all the properties, the area under the loop, that means how wide or how small this thing is there, or the saturation magnetization, the remanent field, and the coercive field, everything are intrinsic properties of the material. But of course, it depends. When I say, okay, for a given sample, okay, even suppose if I take iron I can make a sphere, or I can make a rod, or I can make another shape. So the shape dependent factors do come into the picture. So those things one has to be, because the whole magnetization process, again, I have to go back to your magnetostatic energy, your domain picture. So that will decide how the hysteresis is there. So in that sense, that depends on the shape and shape of the material as well. But for a given shape, for a given material, these values are the same. They don't depend on the external field. Okay?
okay, sir.
Yeah.
Sir, in that hysteresis loop, the starting point is origin.
Yes.
So can we reach that point after, like after doing any experiments?
What do you mean by raising?
No, sir. The starting point for in this hysteresis loop is origin. It's starting from origin.
Yeah.
But after after taking some measurements by increasing
Okay,
field
I'll tell you. Depends where you stop the measurement. For example, again, good question. Suppose I started here. Okay, previous another graph was there, right? Here, let us say. Okay, I started from here, origin, saturated it, right? I came back
Yes, sir.
here. So now, what is my field?
0.
It is 0, right?
Yes.
But remanent magnetization is there, right?
Yes, sir.
So now what I do is I will not complete the loop. I will simply take out the sample from the magnetometer. What do you think will be the magnetization? That will have this value, isn't it? Okay.
Okay, sir.
So now next time, suppose I again insert this sample into the magnetometer. So the starting point will not be here. It will be here.
Oh, okay, okay.
Okay. But it's not that it will go from here to again up. No. From here it will
But,
saturate here only. You understand?
But, sir,
because this is the history dependent. This is the magnetization which is trapped inside the material.
Okay, sir. Then, so if you do it again from that point.
From here, if I do, it will again retrace the same path. Okay, as long as I saturate.
No, sir. At that point, we are increasing external field.
Yes, yes.
Yeah,
see, from here, initially it is here, right? When
yes,
it is 0, you can see my arrow, right? You can see here.
Yes, sir.
So
Yes,
when
sir.
the field is increasing, now it will go like this.
Oh, okay. Retraces the same path.
Retraces the path, and then when I decrease it, again it will come back to this and then retrace the path.
Okay, sir. Okay, sir.
Right?
Yes, sir.
Yeah. So that is what happens. Okay, so I think I'll stop it here, because now the next point is, I mean, magnetism is an ocean. I can go on, but I don't want to do that. So what I'll do is next week we'll start with the experiment. Okay, 2 things we'll do. What we'll do is, like, what is the experiment, and also I'll try to record the video consisting of the experiment, hopefully by Thursday, so I can also show you in the lab, okay, what we are doing and things like that. Okay, and so probably some fun will start. Okay, yeah. So I think I'll stop the recording first, and then if you have further questions, I can answer, and then we can.